Hello, this video is for STA2023 Statistical Methods, Chapter 8. This is going to be a really important video and a really important chapter to kind of get an understanding of this thing we're about to talk about called hypothesis testing. Hypothesis testing is a formal procedure that enables us to choose between two hypotheses when we're uncertain about our measures. Now, how this works is something we're going to have an HO and we're going to have an HA. The HO is the null hypothesis, the conservative, status quo, business as usual statement about a population parameter represents no change, no effect, or no difference. And I'm going to add there that it's always equal. HO is always equal. Now the alternative hypothesis is HA, A alternative. The research hypothesis, it's usually a statement about the value of the parameter that we hope to demonstrate is true. HA is going to be less than, greater than, or not equal to. Now, we also have our alpha, that is our significant level. That represents the probability of rejecting the null hypothesis when the null hypothesis is true. A general alpha is our 0.05. Now, that is like our cutoff. I want you to think of that as cutoff. And again, traditionally it's 0.05, but it can also be 0.01 or 0.10. Now, your test statistic compares our observed outcome to the null hypothesis. Now, that's going to be like our z-score, If the null hypothesis is true, then the z statistic will be close to 0. Therefore, the farther the z statistic is from 0, the more the null hypothesis is discredited. Now, what we're going to find when we do our z-score, that probability, is our p-value. The p-value is a probability. Assuming the null hypothesis is true, the p-value is a probability that if the experiment were repeated, you would get a test statistic as extreme as the one you actually got. A small p-value suggests that a surprising outcome has occurred and discredits the null hypothesis. Now, this is really kind of a lot of stuff at once, so we need to do many examples. So just to give you a first example, let's say I told you that 30% of all people wear glasses. Okay, so your null hypothesis would be p equals 0.30. That's what it's supposed to be. That's the population parameter. That's everybody. Now you're like, oh, many of my friends have contacts, glasses. I don't think that's true. What I believe is I think it's greater than 30. That would be your alternative hypothesis. Now again, how this works is we have a claim. It's supposed to be 30. P equals 30%. That's our HO. We think it's greater than that. Now again, you can think it's 40 or 50. We don't put that number in. What we say is the claim is 30. You're either going to say it is less than 30, which you think it's lower than 30, greater than 30, you think it's more than 30, or if you're not sure if it's less than or greater than, you can say not equal to 30. I don't know what it is, but I know it's not 30. So that's how the HO and HA work. Now, you're going to do the work, and we'll do a bunch of examples, and you'll find, let's say, we did a random study of 500 people, and 250 wear glasses. We found our 50% of people wear glasses. Now, that would be our p hat. 30% would be our p. So we run the numbers, whatever it is, and let's say we get a p-value, which would be the probability. Let's just make that up, 0.01. Now, we could do the math, but this was just for example. Now, our p-value is 0.01. The alpha, our cutoff, is 0.05. If your p-value is smaller than alpha, you reject HO, and it's greater than 30. If your p-value is not greater than alpha, not smaller than alpha, sorry, then you fail to reject HO. Now again, that could be really confusing, and that's why we're going to do many examples. So, notice we have some information here. We're going to still do our condition 1, is it random and independent? Condition 2, the population has to be greater than 10 times the sample size. Condition 3, n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. These are going to be the conditions that have to be met, like we did in Chapter 7. Hypothesis testing has 4 steps. Step 1, hypothesize. Step 2, prepare. Step 3, compute to compare, and then we interpret. And I have this little conclusion chart, which will be really helpful in the beginning. If the p-value is smaller than alpha, you reject HO, then your conclusion is going to be less than, more than, or not equal to, depending on the situation. But if the p-value is not less than alpha, we fail to reject HO. We do not reject HO, and then we're either going to put not less than, or not more than, or not different than. So notice it's either less than or not less than. It's either more than or not more than, not equal to or not different than. Now again, this can be very confusing, but we're going to do many examples, and this is really important stuff. Okay? So let's look at our very first example. It is reported that 23% of Americans have a tattoo. We did a survey of 100 Americans and found that 25 out of 100 have a tattoo. It's a random sample. Is there evidence at the 5% level that 23% or more of Americans have a tattoo? So let's break this down. Our P would be 0.23. 23% of all Americans have a tattoo. You did a study, random sample, of 100 people, and 25 out of the 100 have a tattoo, 0.25. Now the sample size was 100, and our alpha, our cutoff, is 5%. And we're looking to see if it's 23% or more, 23% or more. Now, before we move on, let's really understand this. The claim is 23%. Your evidence is 25%. Do you have such strong evidence to say that 23 is wrong? Now, if we kind of stop, do you think 25 is so far away from 23%? Is that really far enough to say it is greater than 23? That's the question. So we write this up. HO, P equal to 0.23. The proportion of all Americans with a tattoo is 23%. That's the claim. HO is always, always, always equal. HA is what we believe. We believe that it's greater than 23. It's in the problem. It's either going to be less than, greater than, not equal to. This one says greater than. So the proportions of Americans. So again, P is 0.20 equals 0.23. HO, the proportion of Americans with a tattoo, is 23%. HA, P is greater than 23%. The proportion of Americans with a tattoo is greater than 23%. So the idea is the claim is 23. I think it's greater than 23. My evidence is that 25%. Then we have to check our conditions. So when we check our conditions, number one, was it random? Now it should have been stated, so I forgot to write that there. But it should always be stated as random. Then your population has to be greater than 10 times your sample size. All Americans greater than 10 times 100, which is 1,000. N times P greater than or equal to 10. N times 1 minus P greater than or equal to 10. 100 times 0.23 is 23. That's greater than 10. Check. 100 times 1 minus 0.23 is 77. Greater than 10. Check. So all our conditions are met. It should look very familiar from Chapter 7. Then we have to find our SE. To find our SE, it's the square root of P times 1 minus P over 100. Be careful typing that in. You get 0.042. When we find our Z-score, it's 0.25 P hat minus 0.23 P all over our SE of 0.042, which gives us a Z-score of 0.48. So if we're drawing it, it would be probably about here. 0.48 greater than. If you look it up in the table, you get 0.6844. Remember, the table always tells you less than. We're looking for more than. We're looking for more than. So we do 100 minus 6844, and we get 31.56%, or a p-value of 0.3156. Now, we can check this in the calculator. So I haven't shown this before, but I'm going to show you now how to do this all in the calculator. It's a great way to check. So in the calculator, we're going to go to turn it on. We're going to go to stat, to the right for tests. And we're going to choose number 1, Z-test, which is what we're doing. Then it's going to ask us, do we have the data or do we have the stats? Now, actually, with stat test, not a Z-test, that can be used before. We're doing a 1 proportion Z-test, number 5. 1 proportion Z-test, number 5. Then it asks us for proportion, that's the claim, both be 0.23. Now this is where it gets a little tricky. You want to put the 0.25 here, but that's not what the calculator wants. The calculator wants the data, the fraction. And the fraction is 25, enter, out of 100. Okay, so when it asks for x, it asks for in your sample, the numerator, 25, and then n would be your sample size, 100. We think it is greater than, and then we go to either draw or calculate. If you go to draw, you get the nice little picture like we did. And it gives you your z-score, and it gives you your p-value. Okay. Now notice these are a little different because the calculator finds it exactly. We had to round a little bit to use the z-table. Both answers are correct. They're super, super close. The calculator is actually a little bit more correct. So there's your p-values. That's a good way to check it. If you hit graph and you have an error, most likely when you go to y equals, one of your plots are wrong. So if you did get an error, it's because your plots are highlighted. So if you have a highlighted plot, make sure you go up to it, hit enter, unhighlight it. So when you do stat, over to test, number 5, one proportion z-test, put in all your data, hit draw, gives you a nice picture, gives you your p-value and your z-score. If you did hit test number 5 but chose calculate, it just gives you the numbers, which also works as well. Now, what does this all mean? When you get your p-value, you're going to compare your p-value to your alpha. P-value to alpha, and you can use that conclusion chart. But our p-value is 0.3156, our alpha is 0.05. Question is the p-value smaller than alpha? Is the p-value smaller than alpha? And the answer is no, it is not. So, we do not reject HO. There's a 3-part conclusion. Part 1, we do not reject HO. Part 2, why? There is not statistically significant evidence to reject HO. Our p-values are evidence. Part 3, we conclude the proportion of Americans with a tattoo is not greater than 23%. So how to break this down? Sentence 1, either you do or do not reject. We do not reject. You can also say fail to reject. Then, is there enough evidence or not? There is not statistically significant evidence to reject HO. We cannot reject HO. It's kind of restating the first sentence. And then your conclusion goes back to HA. We conclude the proportion of Americans with a tattoo is, now it's either greater than 23 or not greater than 23. We were wrong. We could not reject HO, so it's not greater than 23%. And again, you have a conclusion chart to walk you through this. So if the p-value is not less than alpha, you fail to reject or do not reject. And then we choose not more than in this case. If the p-value was smaller, which is not in this case, but if the p-value was smaller, we would reject HO and say it is greater than 23%. So it depends on what side you're on. Then we can do a confidence interval. So for the confidence interval, because alpha is 5%, we're going to be 95% confident, and that's what it asks for. Remember our formula for confidence interval. It's p hat plus or minus z star times your SE. So it's 0.25 p hat plus or minus z star, which you can use 2 or 1.96, times your SE, which we found above, and you get these numbers. Now again, we can check on the calculator. If we go to stat, test, we did one proportion z-test number 5. Now we're going to go to one proportion z-interval letter A. One proportion z-interval letter A. Again, the calculator wants the fraction, 25 out of 100. Confidence interval, 0.95. Go to calculate, and the numbers are very, very close. So our sentence is, we are 95% confident the proportion of Americans with a tattoo is between 16.6% and 33.4%. Now remember, we were trying to say that it's greater than 23. 23 is in the middle. Our confidence interval is not entirely greater than 23. Our confidence interval is actually verifying that it is 23%. That's why we could not reject 23%. Thank you.